Hey there guys! So I've done a lot of questions focusing on polar-stereographic charts, great circles, and Rhumb lines, etc. I'll now break down a question based on time that has caused a lot of confusion. So here we have a question giving us a lot of information. What we first need to do is to accept the challenge and not panic. The next thing would be to read the whole story and decipher what's going on. It first tells us that on the 4th of February at 0800 hours, standard time at A, an aircraft is exactly above position A. We need to find the time and date of arrival at position B in the standard time at B. Looking at the positions, we can get a few clues as to what this question will require. We see that they are the same latitude, doesn't really matter for time-related questions, and the longitudes are quite large, with one in the east and one in the west. So we'll probably be adding or subtracting a day if we choose to go past the Antimeridian. I'll explain what I mean by this later on. We are helpfully given the conversion to get from standard times to UTC. It then starts to talk about a ground distance of 1736 nautical miles between the points and an air distance of 1636 nautical miles. The difference is caused by a tailwind of 25 knots. To make sense of how that tailwind is causing the difference, the tailwind makes our ground speed higher than our true airspeed, so we can cover a larger ground distance compared to an air distance in a certain amount of time. I will be going into more detail regarding this in the Triangle of Velocities chapter in the flight computer course I will be releasing in the near future. A lot of questions from general navigation, flight planning, meteorology, and instruments use the flight computer, so you will need to become a master with it. Don't get too excited, but it will feature detailed explanations and video walkthroughs on how to solve every ATPL flight computer related question. It will feature things that no other training provider has done before, for example flowcharts that can solve any question from the banks. This will put the fear of what to do for hundreds of questions behind you. Okay, enough of the sales pitch, let's get back to business. As you know, I like visualizing what's going on, so now I'll draw out some sort of diagram. Seeing our positions have large eastern and western longitudes, I'm going to involve the good old Japan and US. We are also given the conversions to UTC, so I'll involve the UK as well. Don't think of UTC as some weird construct, think of it as the time in the UK. Well, it isn't always that time, but for these purposes it's close enough. So we are practically going to be doing time conversions across the whole globe. When we are doing this, a top-down sketch of the globe will be handy. It's pretty much the same as the polar-stereographic charts I drew in my previous videos. As we know, the US is in the west, so I'll put the position A near it, as it has a large western longitude. Position B is in the far east, so it will go near Japan. For the rest of the question, I'll sometimes reference A as the US and B as Japan. Doing this will help you apply the rules that we go through now to other questions. One of which being the idea that the US is in the past. Okay, we're travelling from the US to Japan and have been given distances and speeds, but we need the time. So as in most time-related questions, we will need to figure out what duration the flight is. There are multiple ways to do this, and as you know, I like showing multiple approaches. One is where we work out how long the tailwind is acting for. This will be the same as the duration of the flight. In order to do this, we need a tailwind-related distance and speed. The tailwind makes us travel 100 miles further than our air distance, and the tailwind is 25 knots. With these two values, we just use speed equals distance over time to work out the time. Here we can just swap around the speed and time. If you don't remember how to rearrange equations from school, let me know and I'll consider helping out. Okay, so time equals distance over speed. So we do 100 nautical miles over 25 knots to get 4 hours. Another method, which is what most students would have used, would be the nautical air miles over true airspeed equals nautical ground miles over ground speed ratio. This ratio is a repeat of what we just covered, as we know that the distance over speed is always the time. The reason students use this one a lot is because it shows up in flight planning often, so you do need to know how to use it anyway. This method does require the ability to rearrange formula well, so brace yourselves. Most students remember the ratio rearranged like this. Nautical air miles times ground speed equals nautical ground miles times true airspeed. If we use a bit of common sense, we know that our ground speed will be 25 knots larger than our true airspeed, as we have a tailwind. Therefore, we can write our equation like this. 1636 multiplied by true airspeed plus 25 in brackets equals 1736 multiplied by the TAS. Here we have eliminated the ground speed variable from the equation and now only have one variable in the equation, so we can now solve it. We first expand the brackets by multiplying the TAS and 25 with the 1636, giving us 1636 TAS plus 40,900 equals 1736 TAS. Then we can move all the TAS to one side by subtracting 1636 TAS from both sides. So we get 40,900 equals 100 TAS. Then we divide by 100 to get TAS equals 409 knots. From that, we can use time equals distance over speed, where we use the nautical air miles and TAS. So 1636 over 409 equals 4 hours. Or we could have used the nautical ground miles and ground speed, where 1737 over 434, which is our TAS plus 25, also equals 4 hours. You can do this calculation on your flight computer as well. If you'd like me to go over flight computer related questions, leave a comment down below. Okay, now that we worked out the time in every conceivable way, let's take a look at using that time to solve the question. So starting at A, we have the time of departure, date, conversion to UTC, and the duration of the flight we just worked out. Let's first work out the time of arrival in terms of standard time at A. This is where students trip up. We need to think of two things especially, the first being the event, which is flying from A to B, and the second thing being the time zone conversion. If we add the duration of the flight to our standard time at A, we will get the standard time at A when the aircraft lands at B. So starting in the US, if we add the duration of 4 hours to 0800 on the 4th of February, we will get 1200 hours on the 4th of February. This will be the time in America where the plane lands in Japan. I have put ARR next to the time, as all these times will be the time of arrival. This is helpful so you don't get confused by accidentally adding the 4 hours again, or getting lost and not really knowing if the plane has landed or not. Okay, that is our event covered. Now we need to convert the time zone from standard time at A to standard time at B. Seeing we are told how to convert from UTC to A and B, let's convert from standard time at A to UTC, and then from UTC to standard time at B. You may think, why don't we just go past the Antimeridian as it's a shorter distance? Well, even though the other way round the world is a longer distance, it's an easier way to go for time conversions. So let's set off the long way round, just like Columbus did. So to get to UTC, it's like working out the time in the UK from the US. For my GenNav exams, I remembered two facts that really helped in converting times. Let's say we all live in the UK. Yes, it would help to think that you're from the UK or any country in the same time zone, as you will be using UTC a lot. Now compared to the UK, a country in the West, such as the US, is in the past, and a country in the East, such as Japan, is in the future. This helps you easily work out whether you need to add or subtract the time conversion. However, I want to now check to see if you've noticed something peculiar. If not, pause the video and take a look at the answers and the longitudes to see if you notice something strange. The strange thing is that as we are going from the US, which is in the past, to Japan in the future, and are crossing the Antimeridian, we must be adding a day to our calendar. Looking at the answers, there is only one which is the next day, which is D. So I could have just told you this fact, and we would have got the answer straight away without having to work out the time or any other conversion. But don't worry, I did not waste your time, because this is a video where you will learn how to solve other questions, not just this one. Okay, now back to what we were doing before. As we first want to go from the US to the UK, we will be going into the future, so we need to add the time. So even though we see a -9, we actually need to add 9 hours to our clock to get 2100 hours on the 4th of February. This is the time in the UK when the aircraft lands in Japan. Now we go back to the rule and think, because Japan is in the east, it's in the future, we just add the conversion, which is 12 hours, to get 3300 hours on the 4th of February. Wait, what? 3300 hours isn't a real time. That doesn't matter, because we only use it for our working out. As we have too many hours, and are actually in the next day, we will need to subtract 24 hours and then add 1 day to our calendar. So 3300 hours on the 4th of February becomes 0900 hours on the 5th of February, therefore reaching our answer D. Thanks for watching my video. If you want to see more things like this, please like and share the video with your buddies and the communities you are within. I want to spend more time doing things like this so I can release more videos and improve the quality of my content, but can only do that with your help. Thanks again, and see you soon.